So today is our last day of classical thermodynamics. And chemical reaction equilibrium, I think, is a reasonable bridge because in all of the other classical thermo that we've been working on, we haven't been discussing sort of any of the molecular properties. How's everyone doing today?
Good.
Good.
I'm listening, I promise.
So the formulation that we've constructed is to create an equilibrium constant that's going to vary as a function of temperature only. Now the reason why it varies as a function of temperature is because we have defined this based on a standard state. This is effectively the delta G of the reaction. Where we said that the Gibbs is based on if the fluid is at pressure of 1 bar, it's the pure fluid. I'm sorry, I believe. Oh no, sorry, second approach. This is, no, I have that right. Yeah, because in this case here, G over bar, these are equal, because they're both at the same composition. I was just making sure I got my nomenclature correct. Okay, so this is the formulation that we've constructed, and we set this equal to a product summation of activities, where A of I is equal to the activity. We define this as the partial fugacity divided by the partial fugacity at the standard state. So this is going to be a function of temperature, pressure, composition. This is going to be a function of temperature, pressure is fixed, and composition is fixed at 1. So effectively, it's just a little mathematical trick. So what we can do then is that our equilibrium constant is only a function of the Gibbs as a function of temperature. Whereas on the right-hand side, it's going to be a function of our complex multi-component phase equilibrium. Now I had a handout, and the Sandler book has a nice handout, albeit a little bit complicated, that tells us how to approximate the activity, but in many ways it's just a restatement of how we approximate the partial fugacity. So the same thing in vapor-liquid equilibrium. The only complication, however, is that it's not just the partial fugacity, it's the partial fugacity divided by the standard state partial fugacity, which means that every time we deal with pressure, since we've chosen pressure of 1, that basically means that we have to always have that 1 bar pressure in the system. Okay, so what we're going to do today is we're just going to quickly go over how we can apply this to solve a real reaction equilibrium system. And then we've got some example problems that we can have everyone set up. So the nomenclature for chemical reaction equilibrium is convoluted and a bit confusing, but how we actually apply it is very systematic, and it's not too bad. And this will likely be a review for most everyone who's seen this before from chemical engineering. So let's say, for example, we have some arbitrarily complex reaction. We'll say this is an ideal gas phase reaction, in which case the activity is going to be equal to what?
Partial molar fugacity of I, which is Y times P, right?
Okay.
Yi times P.
That's going to be the numerator. What's the denominator?
1 bar.
1 bar. So, how I solve these is build a big table. Exactly the same way that I would necessarily solve it in a computer. So I wouldn't actually do any algebra on paper if I was trying to solve this myself. This would all be done in a computer. So species, we have A, B, C, D. Let's say we feed a stoichiometric ratio to the system. So in that case, the initial moles would be 2, 1, 0, 0. Stoichiometric coefficients, -2, -1, 3, and 1. The number of moles of species I at any arbitrary point are going to be 2 minus 2 times the extent of reaction. Right? In this case here, it's just a general formula where it is Ni naught plus the stoichiometric coefficient multiplied by the extent of reaction. So if I were doing this in Excel or any other computer program, I would have x is equal to, let's just say, 0.5 as an initial guess. I know it's not necessarily going to be 0.5, but I'm just going to plug in that value, just as a placeholder so that these have values. Then we march our way down. 1 minus the extent of reaction. This is 3 times the extent of reaction. This is the extent of reaction. All I'm doing is applying this general formula. Now in this case here, we'll have the total. In this case, we see that we have 2, 1, 3, 1. That means we have a positive 1 summation of the stoichiometric coefficients. That means as the reaction progresses, we're creating more moles. Now we add all of these up. Let's see. I have it as 3 times the extent of reaction, meaning that we're starting off with 3 moles initially, and that every time we have an extent of reaction, move everything from the left-hand side to the right-hand side, we are creating 1 more sort of mole in the system. The mole fraction is then just going to be the number of moles of species I divided by the total number of moles. Again, there's no reason to ever do this by hand if you've got a spreadsheet. So in a spreadsheet, I would just basically take this value divided by that value. But in the case, for example, we'll just write it out. 2 minus 2 times the extent of reaction divided by 3 plus the extent of reaction, and go on and so forth. And then in your code, this should sum up to equal 1, just as a consistency double check. Now, this is our chemical reaction equilibrium relationship. We are approximating this as the product sum based on an ideal gas phase reaction. This is our approximation for the activity based on the fact that we are going to be assuming it's an ideal gas. Now, if this were a liquid, this would be the mole fraction multiplied by the saturation pressure, which would be divided here and cancel out. If it was non-ideal, we would have an activity coefficient, for example. So now it's basically just a plug-and-chug type problem. Whether or not this is a constant pressure or a constant volume reaction is going to necessarily determine how we're going to solve this problem. So let's just go ahead and substitute. So we have equilibrium constant as a function of temperature. This would be determined based on looking up Gibbs free energies or calculating Gibbs free energies of the pure species. And so let's go ahead. So we have y of c pressure cubed, y of d pressure power 1, y of a times the pressure squared, y of b times the pressure raised to the power of 1. Positive stoichiometric coefficients for the reactants in the numerator, negative stoichiometric coefficients for the denominator. So we have mole fraction of c cubed, mole fraction of d to the power 1, mole fraction of a squared, mole fraction of b to the power 1, and you have an imbalance here. We're left with the lingering pressure. Sorry. Now, if this is not a constant pressure reactor, we would substitute in an equation of state for the system pressure. And there we have it. One equation, one unknown, because all of the mole fractions are going to depend on the extent of reaction. Even the total number of moles is necessarily going to depend on the extent of reaction. Sorry, this one here. 3 plus extent of reaction. So it's non-trivial to do by hand, but on a computer it's really straightforward. So when I solve these out, I will build this in the Excel spreadsheet. I won't write out any of the algebra myself, and I will just basically use that to solve everything. All right. So let's do these example problems. So the example problem, relatively straightforward reaction. This is a far more complicated one. It is just A equals 2B. So this is kind of a dimerization reaction or an inverse of a dimerization reaction. So question 1 says we have NA naught is equal to 1. The number of moles of B initially is also equal to 1. And pressure is constant. For part 2, it's the same, but pressure is not constant. And then part 3 rather, in this case we have, let's see, 4A, 3B initially, and 10 molecules of an inert gas. So what I'm looking for is this expression. Now for this complicated reaction, obviously it's much bigger, but for the simple reactions, it'll be much more small and compact. So let's take a few minutes. Everyone will go through and provide to me the equilibrium expression that we can use to solve for chemical reaction equilibrium. So derive this expression, but for that reaction under those conditions. And for some of the latecomers, raise your hand if you have any questions. Assume ideal gas phase reaction. So in my solutions, I took it one step further than here. I actually substituted these values into this expression to get it to be one equation, one unknown.
One question, what is VI?
That is the stoichiometric coefficient. This one here, you mean? Yeah. So it's going to be negative for the reactants, positive for the products. And that's why you have, in the equilibrium formulation, products over reactants. looks like everyone's making pretty good progress. The nice thing about it, it is pretty algorithmic. Let's just go over question 1 really quickly. So again, let's build our table. A, B, stoichiometric coefficient, number of moles initial, number of moles, and the mole fraction. So stoichiometric coefficient for A, -1, for B is 2, number of moles initially is 1 and 1. We apply the simple formula, 1 minus extent of reaction, 1 plus 2 times the extent of reaction, which means the total number of moles here is going to be 2 plus the extent of reaction. We're starting off with 2. So that means our mole fraction is going to be 1 minus the extent over 2 plus the extent. In this case, it's going to be 1 plus 2 times over 2 plus the extent. And let's just verify this, that adds up to 1, so that we need to have 2 plus the extent of reaction. So we have 1 minus, 1 plus. This actually does end up add up to 1 no matter what. If you look at the numerators. Right, so we just need to make sure that the numerator equals the denominator. 1 and 1 gives us 2, minus 1 and 2 gives us 1 for the extent. So it actually all works out. Then we apply our equilibrium expression. And then it's just a matter of substituting in our expressions. So for B, we have 1 minus the extent, oh sorry, B, sorry, my bad, is 1 plus 2 times the extent squared over 2 plus the extent squared. And then for here, we have 2 plus the extent over 1 minus the extent multiplied by the pressure divided by 1 bar. This cancels with this. So if you were doing this out by hand, I don't know why you would ever want to do this. This is the expression that we would be solving for. One equation, one unknown, unless I've made a mistake. No, I think I got it. Now switching over to part 2, if the pressure is not constant, then all we will be doing is substituting P is equal to 2 plus the extent of reaction RT over V, so we would need to know the volume of the reaction necessarily. So if we substitute that expression in, this would cancel with that. Oh, I wrote this wrong. This is actually 2 moles of B, as I've written in the problem's example. But it doesn't actually affect the final answer, because it all cancels out.
One question.
Yes?
What is the expression P over 1 bar?
This is because that's a common thing to be left out. When we're approximating the activity is not just the partial fugacity, it's the partial fugacity normalized by the standard state partial fugacity, which has been adopted to be 1 bar pressure for an ideal gas system. Well, actually for any system. So that means when we're doing the chemical reaction equilibrium, in order to set up the equilibrium constant in this way, that we have to use that. Because we're calculating the Gibbs of the pure fluids at 1 bar pressure.
So we'll include that 1 bar in our calculations for cancelling.
Yeah, so if I gave you units in kilopascals, you have to go to bar. It won't work out unless you have it in the right units. Now, sometimes it works out because the pressure's in, it doesn't matter. There's no pressure dependency, but if there is, then you have to consider it. Okay, now the last one, I'm not gonna go over it, but I can provide the final answer. The only complication when we have an inert, just for the interest of time so we can talk a little bit about stat mech, because I feel like, does anyone have any serious questions about chemical reaction equilibrium? Or do we all feel pretty comfortable with it? So I know those who are chemical engineers have probably seen this a bunch of times over again. So the only complication with the third part is if we add in an inert. In this case, its stoichiometric coefficient is 0, and then that's it. You basically turn your brain off and apply the same formula, the same algorithm. So in question C, it says that there's 10 moles of an inert, which basically means that the number of moles of species I is always going to be 10, which in this case, if we were to apply it to the conditions of the other problem, right, that would mean that we would have a total of 12 moles plus the extent of reaction, and then it would just modify, you know, it would just change the denominator. So adding in an inert will just slightly play around a little bit with the equilibrium. But the approach is exactly the same. Yeah. But depending on sort of the pressure of the system and whether or not the moles go forward or back, it can change things a little bit. So an inert is generally not introduced into the reaction necessarily for modifying the equilibrium. An inert oftentimes is introduced for absorbing energy in a highly exothermic reaction. But it's a nice example to have to complicate this a bit. Okay, any particular questions on chemical reaction equilibrium? I think we have one more latecomer. So with that, it concludes classical thermodynamics. And now we can move on to statistical thermodynamics or statistical mechanics. Now, if we were to say, for example, be introducing any more complexity in classical thermo, meaning multiple types of simultaneous phase equilibrium or reactions with phase equilibrium, ultimately it all just breaks down to strategies. We've covered all of the fundamental equations of classical thermodynamics. So the only complication is just solving more equations at the same time. So for me, I've never been a fan of tedium, so I like to kind of end things there with classical thermo. Now some classes you could go through and do build some sort of a reactive distillation process and try and solve it, but it's really just an exercise in numerical methods at that point. How do we approximate these complex expressions? But instead, we're going to talk about StatMech, because I think that gives us a new conceptual perspective on the topic. So, statistical mechanics was developed in the late 1800s and early 1900s. The objective was to translate our understanding of classical thermodynamics to atomic theory. Classical thermodynamics has been around since about the 1600s, right? It became more developed and more mature as things moved on, right? But the second law was sort of being codified a little bit more clearly around the same time, so they kind of mixed it a little bit. But in general, classical thermodynamics got better over time. This was the gold standard. This had been used to power the Industrial Revolution. It had ushered in sort of a new era of the modern era. Now, atomic theory, well, let's see. I think the electron and neutron and all that was discovered, let's say about approximately 20-ish. Right, so we've got a lot of history in classical thermodynamics that is now going to be married with this idea of an atom. So the first real concrete sort of theoretical evidence for supporting an atom was from Boltzmann and Maxwell, where they developed the kinetic theory of gas. By modeling a fluid as particles moving, right, with a particular velocity, what that allowed them to do is basically say that the temperature was the kinetic energy of all the particles, and that the proportionality relationship between energy and temperature is the Boltzmann constant. Right, so the Boltzmann constant, 1.38 times 10 to the negative, I think it's 23, joules per Kelvin. So this is sort of the number that got Boltzmann in trouble. It was a very, 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 very small number, right? Now, Avogadro's number, the gas constant, is just the Boltzmann constant multiplied by Avogadro's number, so it's just scaled up. But what this meant, basically, was that the proportionality relationship per particle was very, very small, meaning that an atom had to be extremely small. And that's why it was basically viewed necessarily as a mathematical construct, because people knew that this was too small a particle that we could ever visualize it. It was so small that they kind of assumed that it didn't actually matter whether or not they were real particles or mathematical approximations. Right? Because they view this as too small to ever be able to be seen. But if we are to look at the collision of a particle with a surface, what Boltzmann's atomic theory was able to do, it was not only able to describe what the temperature was through the Boltzmann constant relating to the kinetic energy, but it was also able to describe what pressure was. So if you recall from classical thermo, both pressure and temperature are defined based on partial derivatives of entropy and internal energy, right? So in the case of a real atomic system, let's say we have a temperature of 300 Kelvin. That means the energy of every single collision is on the order, this is a notation, I don't know if you guys have seen this before, but big O, just sort of as a ballpark number, of kBT, right? The Boltzmann constant is the proportionality between temperature and energy, and it's related to the kinetic energy. So when a particle hits a surface, it's going to be hitting the surface with the energy proportional to that theory. So that means that the energy per collision is going to be approximately, or on the order of 10 to the minus 21 joules. Meaning 10 to the 23 multiplied by 10 to the 2 gives us 10 to the 21. That's a very, very, very small amount of energy. However, the number of collisions is on the order of 10 to the 24 per second. No, this is actually per centimeter, so let me get these right. This is 10 to the 24 per centimeter squared per second. So it's a large amount of collisions. So then again, if we look at the energy of the collisions multiplied by the number of collisions, that gets us to a situation where we're on the order now of 10 to the 3 joules per centimeter squared per second. And this is sort of just really quick back the envelope analysis. But this now is what we would consider a reasonable finite value, right? On the order of hundreds or thousands of joules worth of energy. These are numbers that were very rich, typical to see. So the hard part of StatMech is this part right here. How many billions is 10 to the 24? What is a billion?
10 per 50.
So a billion is 10 to the 9. So this is, let's see, a billion, billion, a million, billion, billions? Right, is that right? So you have 10 to the 6, 10 to the 9, 10 to the 9, 18, 24, yeah. So 10 to the 24 collisions per centimeter squared per second, which, right, per centimeter squared per 1 second is a million, billion, billion collisions. Okay? So it's a big number. Now, I don't know how old my notes are here, but the world's fastest computers. Now we measure those in things called flops. Does anyone know what a flop is? It's a floating point operation per second, right? So that would be adding two numbers together would be a flop, right? Taking the square root of something is not a flop, right? It would take multiple ones because you have to approximate it somehow. So, I don't know exactly when my notes were taken here, so it's always a competition, but the fastest computers are on the order of, let's say, 100 petaflops. Right, and peta is 10 to the 15. So the world's fastest computer can calculate, in this case it's only a million billion, right, calculations per second. Which basically means it would take biggest hand wave approximation in the world right here. That means it would take, so in that case, peta is 10 to the 9 and 10 to the 6. Which means we're still left with a billion particles. So it would take 8 billion, seconds, let's say, to even calculate 1 second of collisions with a wall. Now this is a vast oversimplification because it does not take one flop to calculate the behavior of one particle. It takes many, many, many more calculation cycles to do that. You have to calculate the energy between two particles. You have to sum that up for all the other energies in the system. You have to then integrate it using some sort of a numerical integrator. Then you have to repeat that process over again. Okay? So the idea here, though, is that we're even now considering with modern computational speeds and powers. Modern computational speeds and powers, right? This is the world's most powerful supercomputer. Now there's probably half a dozen of computers that are pretty close to this. Right? Cray Titan at Oak Ridge is probably, I think, America's most powerful one. I believe this one here, I think I updated my notes last year for this one. This is based on the number of IBM's top 500 computer. And I think it's a little bit cheating because this is not actually one computer stored in a warehouse. It's a distributed computational network. So it's kind of like those things where you can sign up and say like, oh, if I'm not using my cell phone, you can, mine Bitcoin on it or do protein folding games and problems like that. So I believe these are the numbers from the IBM top 500. I don't exactly know the details of that supercomputer, but it's not a conventional stored in a giant warehouse with lots of wires type computer. The record for that style, I believe, is held by a computer in China. Yeah, Oak Ridge's was the world's most powerful as of, I think, like 2015 or something like that. Okay, so it's not possible. We really cannot, even with today's computers, even comprehend the most smallest of macroscopic size systems. Right, so simulating a room full of particles is just a fool's errand. There's no point to doing so. So, what we have to do is we have to use statistics. So the idea behind StatMech in a nutshell, follows kind of this general procedure. Is that on paper, we will propose a model for how atoms behave. Now this could be a lattice model and basically say, okay, we're going to build a big grid. And we're going to say that particles can only be on the axes of this grid. Okay? That's a finite size system. What we'll do then we'll calculate that small system's basic properties. Okay, what we'll say is, let's say hypothetically, we'll go with that example. We will build a grid, and we will put particles inside of that grid. Now, what we'll be talking about in the next couple of days in class is how do we calculate the basic properties of a finite size system. We have to learn a new nomenclature. So one thing we could say is that the entropy is proportional to the number of configurations in the system. And this is where you get the famous Boltzmann equation, W is equal to K B ln omega. That's what that equation means. This omega here is called the partition function. This is the number of configurations in an NVE system, so the number of particles, constant volume, constant energy. You scale it by the Boltzmann constant. This gives you the entropy of the system. Boltzmann used the notation of W for entropy as opposed to S. This is the famous Boltzmann entropy equation. The next step could be, what is the internal energy of this system? So what we can say is that anytime we have two particles touching, they have an energy of negative epsilon. So that means that the internal energy of the system would effectively be just adding up the number of pairs of interactions that exist in the system. Right, that's how we would calculate the basic properties of a simplified system like this. Then the next step, generalize. We would then generalize this to an arbitrarily sized system. So what we could say here is that we have n grid positions by m grid positions. So that the number of vacant sites would be n multiplied by n. Then we use probability and combinatorial statistics to then figure out how many configurations in the system are there. And that's where the combinatorial probability statistics comes into StatMech. And the last step is, if possible, basically, right, so the next step is you want to scale it to the macroscopic system size. So make n an Avogadro's number. Now sometimes that involves using a continuum approximation, sometimes no. But in general, when we scale to macroscopic size, what we do in statistical mechanics is we ensure that the energy and entropy models that we use have functional forms that have defined limits of integration or summation. So if we can, if the step sizes of these energy levels are really, really small, we then take these finite particles and then we approximate them as a continuum. So for something like a harmonic oscillator, right, which is the energy modes of vibrations, those energy states and energy levels are too far apart that we can't actually approximate it as a continuum. So in this case, we've adopted something called a harmonic oscillator model, which when you sum up all the energy levels, it converges to a finite value. It doesn't diverge. In the case of kinetic energy of gas particles, the energy levels there are very, very small. So we don't actually sum them up individually. We instead just integrate them because the step sizes are so teeny. So that's the general idea behind StatMech. So now basically what we need to do is introduce a couple of key concepts or nomenclature that we can sort of frame the discussion around. a microstate versus a macrostate. What we care about is the macrostate. This is the time averaged property for a virtually uncountable number of particles. What I've drawn here, this represents a microstate. This represents one possible configuration that all of the atoms, let's say for example, in this room could have adopted. So what we need to do then is recognize that one macrostate has, in our case, a virtually uncountable number of microstates. But in order to apply statistical mechanics, according to our general approach right here, is that we need to be able to generalize all of the microstates to an arbitrarily sized system. And this is where StatMech gets a little bit more complicated. So what we need to do then is that every microstate has to have the same properties to the macrostate, in the sense that it has to have same particles, it has to have the same volume, it has to be sort of interacting and existing in the same space, and it has to have the same energy. But the key thing is that, so if I build a system where I have the same number of particles, the same volume, and the same energy, we have to recognize that there are many, many microstates that have the same energy as a macrostate. So for example, if we just have a particle in a box situation, we could have, let's say, a collection of particles all moving with exactly the same velocity. In this case here, the velocity of each of the particles could be equal to the average velocity of the whole system, in which case the energy of the system would just be the number of particles multiplied by 1/2 mass times by the average velocity squared. That would be the total energy of the system. Atoms don't actually behave this way. You could also envision a situation where you had most all of the particles completely stationary and one of them was just going really, really, really fast. In which case there, that the internal energy would be equal to one particle, mass of that one particle traveling at the max velocity squared. Now, technically speaking, these are both microstates that are consistent with the macrostate. So when we're counting up all of the possible configurations of the system, this is one of the configurations that we would have to consider. As it turns out, when we derive Boltzmann's distribution, we'll actually find out what the real kinetic state, or sorry, what the real distribution of velocities are in a gas, which is what the Boltzmann equation is for. Okay. So when we are defining a microstate, now this is from a classical mechanics perspective, so we're not considering quantum mechanics at all. So from a classical perspective, defining a microstate means knowing the position of all of the particles in the system, right? Where this here is going to necessarily be a set of positions. Right, so the notation that we'll kind of be adopting here is that R vector is going to be the set of positions of all of the particles. Right, so in this case here, this could be the x, y, z coordinate of particle 1, the x, y, z coordinate of particle 2, x, y, z coordinate for particle 3, and so on and so forth. We would also need to know the velocity of all of the set of particles. This would be the velocity vector. What is its x, y, z velocity for particle 1? the x, y, z velocity for particle 2, so on and so forth to the x, y, z velocity for particle n. Now with these two coupled together, you have a full description of the system itself. The velocities give us access to the kinetic energy of the system, which for the most part is going to be the lion's share of the energy, for a low density fluid rather. And then with the positions, that'll tell us not only what the entropy of the system is going to be, but it's also going to let us know if we have interactions between the particles, what is the relative positions of the particles, so that we understand what is their attraction or repulsion. Now I guess in essence you could maybe have maybe an orientational dependence here, but for spherically symmetric particles this would fully describe the system for sort of little balls bouncing around. Now, the one complication for atoms, in this case here, this is for, if we wrote this for distinguishable particles. Atoms are indistinguishable from one another. This is a fantastic long word that you only really encounter in StatMech. So what we mean by indistinguishable is that if I were to swap particles 1 and 2, it would be exactly the same system. Because I cannot label particles as 1, 2, 3, 4, and 5 if they're of the same element. However, if we had a mixture of, let's say, argon and neon, those two particles would be distinguishable. What is a way that I could distinguish between argon and neon?
Radius.
The size of the particle, potentially. What else is different?
Mass.
The mass is going to be different. Probably the easiest way is by its electronic properties, looking at how it interacts with X-rays. Right? What's the spectroscopy? That's probably the easiest way to do it. So the reason why atoms are indistinguishable is because of which principle? This is actually quantum mechanics principle now.
Is that Bohr? No, it's not Bohr. Approximation.
The Heisenberg uncertainty principle. Now that principle states that the uncertainty in the position, right, this is sigma of x, multiplied by the uncertainty in the momentum, which case we can think of this as velocity, is going to be related to Planck's constant. Does anyone know what Planck's constant is?
Like you measure this.
What is the meaning for it?
How do they define mass? Was it kilogram?
It is the minimum quantized energy level. You can never split energy levels below Planck's constant. And it happens to be 6.63 times 10 to the minus 34 joule seconds. Very, very, very small number. Right? Even compared to Boltzmann's constant, right, which is 10 to the 23, this is like a trillion times smaller, right? So that basically means that the energy levels of an atom are extremely small. So for kinetic energy, you can effectively treat kinetic energy velocities as a continuum. Okay. So what the uncertainty principle says here, and then let's just define momentum really quickly. Right? Momentum is just the mass times by the velocity. In this case, it's a vector, so it's a dot. So what the Heisenberg uncertainty principle effectively is saying is that if we have a series of indistinguishable particles, right, we know they're indistinguishable because of the uncertainty principle, I cannot label this 1, 2, and 3 because after some delta t elapses, if I knew where my particles were, I wouldn't know what their momentum was. If I knew what their momentum was, I wouldn't know where they were. So after some time period elapsing, I cannot tell which one is which anymore. It's just not physically possible. So what this concept of indistinguishability does is that when you're trying to basically develop a finite system and calculate the basic properties, you have to recognize that if I were to take two particles here and swap them, that would be exactly the same system configuration. So you have to deal with this concept of indistinguishability. Now, when you are mixing two things, let's say, for example, argon and neon, if you're mixing those together, they are distinguishable. So if I were to take a chamber of all particle of type A and all particle of type A, if I didn't have indistinguishability, I would be generating entropy every time two particles were near each other. If we contrast that to a system where they're distinguishable, then StatMech should be predicting that entropy is being generated. This case here, StatMech should predict that entropy is not being generated, and here, StatMech should predict that entropy is, because you're mixing two particles that are distinguishable. Okay, we are out of time, but the one last thing that I will mention is that we'll talk about the two postulates of StatMech. I'll write them out more clearly. The first one is something called the equal a priori hypothesis, which basically means that all microstates of the same energy are equally probable. Meaning that they have an equal probability of existing. This is the cornerstone of statistical mechanics. If we do not invoke this hypothesis or this principle, we can't do any of our calculations. As it turns out, it works pretty well. The second one, that is the foundation of StatMech, is called the ergodic hypothesis. Has anyone heard of the ergodic hypothesis before? Yes. Hopefully you have. If you read StatMech books, you should account that one. So the ergodic hypothesis basically says that according to thermodynamics from a molecular perspective, we cannot or should not differentiate between a statistical average of configurations and a time average of configurations. Right? What that basically means is that if I take a small system size and I watch it for a very long period of time, that's the same thing as looking at a big system size and cutting it into little sort of subgroups. That's what the ergodic hypothesis says. But I'll talk about it in a little bit more detail, but I just wanted to get to that concluding kind of formulation of StatMech. So the idea here is that we'll spend a lot of time kind of on lattice models or particles in boxes because those are simple systems. Real systems are really hard to calculate with StatMech, but they give us sort of an area of space to test out hypotheses and theories. All right, so we're on to that. We have a quiz on Friday. That's going to be not on StatMech, but all on chemical equilibrium and reaction equilibrium. Sorry, phase equilibrium. Okay. All right, see you. Have a good week.